Well, hi guys, it's terrific to be with you again. We're going to cover today, the exciting topic of vector proofs part 2, which helps to round it off, put it in perspective and give you an idea of the way you should think and the types of questions that they're likely to ask you. Let's go. Okay, we've got here a diagram showing a rhombus. This is an exam question. We've got two vectors A and B shown there in the diagram that you can see. And what does it follow? What follows from all this? So you've got to basically sort the wheat from the chaff out here. Let's put some stuff on there so you can see what you're doing. I've shown this is also vector B, this is also vector A, and I've shown all the side lengths being the same as each other. Okay. Now, have a quick look. What looks obviously wrong? Well, I think A looks obviously wrong because A dot B can't be 0 because the angle between them isn't 0 and they're not 0 vectors anyway. I mean, they're not perpendicular is what I mean. So it can't be 0. Right, A equals B, no, different directions, no good. Now C is an interesting option. You've got to sort out what that means. This is typical of the examiners. They try to confuse you by giving you all this very bewildering stuff. Now come on, what's A? Tail of A, add B. That's a diagonal, yeah? That's the long diagonal. Now, probably the other one's the other diagonal, I'd say. So, A minus B. Look, I think we might go minus B plus A. Yeah, that gets us this diagonal here. So they're asking us, is the dot product of the diagonals 0? Well, for a rhombus, it is 0 because you have to know that for a rhombus, the diagonals bisect each other at right angles, and that doesn't happen in any other kind of parallelogram except a square. Rhombus and a square. Square is is actually a special rhombus, so they're both rhombuses, but not for a normal parallelogram. So yes, option C is correct, and you have to know why it's correct. Okay, so do you know it now? For a rhombus, the diagonals bisect each other at right angles. Yes, so therefore the dot product would be 0. Okay, so are D and E wrong? Hope so. Magnitude of A plus B is not the same as the magnitude of A minus B. No, that's completely wrong. The diagonals have different lengths. And the last one is just silly. A plus B. A plus B gets you vector AC, and that's twice that, so that doesn't equal 0 at all. Okay, so there you go. You've just passed your first exam question of a vector proofish kind. So there you go, option C for you and me. Fills us with glee, yippee. This is an exam question. It's got a vector proof in it. That's why I picked it for you. It's the only question I've ever seen in an exam with an actual vector proof. All right, we've got a triangle with vertices O, A, and B. O is the origin. Vectors O, A. That's vector O, A. That's vector O, B. We've got to show. What have we got to do? We've got to find vector M, A. M is the midpoint of line section OA, so it's there to there. Oh, it's just going to be half A, isn't it? Half of little a, that's very easy. Good. Over the page. Now, same diagram, but this time vector B, A. Well, VA, that's easy. Let's just go from the tail. B's the tail. It'll be minus B plus A, I think. Won't it? Yes, that's right. Yes, very good. Excellent. Okay, good. Cooking. Oh, what's this one? AQ, where Q is the midpoint of the line section A to B. Okay, AQ. Well, if we worked out A to B, and then just did half that, you'd get AQ, wouldn't you? I think so. So, there it goes. Yes, that's that. And that gets us... Yes, that's right. A to B. Yeah, we did B to A above, so A to B is going to be minus that. So it's half of minus BA, which being AB. Correct. Correctamundo. Good. Now, what do we got to do now? We've got to let N be the midpoint of the line section OB. And what are we going to do then? Use a vector method. Ooh, here we go. To prove that the quadrilateral MNQA is a parallelogram. Well, let's put that in, guys. There it is there, okay? So that's what we found out previously, that M was that point, N was that point, and Q is that point there. Now we're going to prove that's a parallelogram. So how do you prove that? That's what I want to. That's what I need to ask you. How do you prove that with vectors? That's where you've got to get your vector hat on, your vector head going. Well, what I've said here is that vector MA is half of little a. We found that in the previous part, A1. So that is a half of little a. Yeah. So now I'm going to explain to you what I need to do to prove that that MNQA is a parallelogram. I say that basically we need to show that only one pair of opposite sides have equal lengths and are parallel. And if you've got that, then the other pair must also have equal side lengths and must be parallel as well. Now, I've done a little diagram above to show you why I believe that's so. Okay? Right? Have a look at this. There's a couple of parallel lines of equal length. Now, can you see that if you have that situation there, they're parallel and they're equal in length, and the sides which join up those to make a parallelogram, they have absolutely no choice but to also be pointing the same way and to have equal lengths as each other, don't they? Yeah, they do. So therefore, what I'm saying is that I'm going to just prove, what I'm going to actually do is I'm going to prove that MA is the same vector as NQ. And if I do that, I've proved a parallelogram. Okay? That's all you've got to do. So NQ is NB plus BQ, and just go through the motions. BQ is a half of BA. Yes? Which is, and we've already found BA in a previous part. So that's why this is an unfolding story. So you use information that you've found in the previous part, looking back, just keeping a little bit of a running sheet going in your head of what you've found and what, that might lead on to what you're doing now, because it always does. Alright, so that's from that part there. So what have I got? I've got, therefore, NQ is NB plus BQ, which is going to be, that's NB is a half of B. That's a half of B. That's the thing we just found in the previous line. And if we just expand that bracket out, what do we get? Hooray today, we've got it, See, look, they're the same thing. MA and NQ are the same. Therefore, we're laughing, guys. We're saying that, therefore, hence, MA equals NQ. And because of that, therefore, the quadrilateral MNQA is a parallelogram. And Mr. Box is coming to congratulate us. Thank you, Mr. Box. You're the man, or you're the box. So now, let's keep going. We're on a roll here. Now we have to consider a particular triangle, OAB, where OA is that thing enunciated up there. Did you know that the Latin word for nuncius is an announcer? So that's where when you say enunciating, you get it from there. All right, so sorry about that. I love Latin. So OB is equal to alpha I, where alpha, which is greater than 0, is chosen so that the triangle OAB is isosceles with OB equals OA side length. So I always draw a picture. It's just essential. OA, OB, and they have to be the same length, which means this is very... Do we just have to find out what A is? Show that A is 4. Oh, that's absolutely easy. Because, look, we can work out the length of this by Pythagoras' theorem in 3 dimensions. And that should work out to be 4, that length. So that's what A would be, because they're an isosceles triangle with OB, length of OB equals length of OA. Same. Easy as. So, let's go through it. Yes, that's Pythagoras in 3 dimensions for the length of OA, and that's going to be that, oh, good show, 4 units. Therefore, that's what? Alpha must be 4, because OB is 4 units long as well, because they told us so. There you go. Yeah, therefore alpha is 4. Well, that's beautiful. We've done it. Mr. Box, thank you. And the next bit. Show that, find OQ, where Q is the midpoint of line section AB. Okay. Alright. We can do that. We'll first of all find AB, then we'll halve that to get AQ, then we'll go from O up to A and then A to Q to get the vector OQ. q. All right, that's what you've got to do. You've got to keep your head with this, and don't miss the point, and don't only answer half the question by working out AQ, which is what a lot of students would do. Okay, so be careful and reread the question before you leave it. AB is AO plus OB, AO plus, wait a minute, from A to O, from A down to O, and then from O up to B. That's what AB is, and we'll do that. There we go. Yeah, and you've got to add OB, which is 4I, because alpha is 4, and we get that. That's good. Now that's AB. So now we've got to get AQ. Here comes AQ for me and you. Half of AB, so just put a half in front and a bracket. Get that? Now we've got AQ. Now we've got to go from O now. So OQ would be OA plus AQ, and OA is all that. Oh, I've actually worked it all out. Yeah, I've actually worked it all out. So there's the answer, right? Got it? So now what we've got is OQ, remembering that we might have to use that in a subsequent part of the question, because all these things lead onto each other, these kind of questions. So, righto, we got AB, we got OQ, we got all kinds of things here, so let's keep going. Now, use a vector method to show that OQ is perpendicular to AB. Oh, well, there you go, you see? We've got OQ from a previous part. We've got AB from the previous part. Looks like we've just got to dot them together and prove the dot product equals 0 to me. That's pretty easy, isn't it? So therefore AB is that, OQ is that. Let's dot them. Let's dot them, guys. And what do we get? Oh, I hope we get 0. I think we're going to get 0. I think we are. Here it comes. Yes, that looks suspiciously like a 0 to me. That's 3.5 minus 3.5, and it comes to 0. Beautiful. Okay, so therefore I just say, just to be completely pedantic about what I'm saying because neither vector AB nor OQ is a 0 vector, and because the dot product came out to be 0 anyway, therefore what am I saying? I'm saying therefore the vectors must have been perpendicular to each other, because that's the only way you'll get a dot product equals 0 if the vectors in and of themselves aren't 0 length. Yes, that's it. Okay, happy? Alright, very good. So that's the end of that question. It had two little vector proofy bits in it. Yeah? Okay. So here's another question, multiple choice question. Looks ghastly. Have a look at it. Have a look at it. We've got some vectors up there, and we've got a funny looking head-to-head angle here. Head-to-head angle, which is not a tail-to-tail angle. We've got to sort that little bit of a conundrum out. And what have we got over here? We've got all these options, and they're all in terms of c squared. C squared. And then on the right-hand side, we've got a squareds and b squareds. Good heavens above. Well, I think we just put one foot in front of the other. First thing which is confusing me is this head-to-head thing. I need to basically make that tail-to-tail. So what I'm going to do is I'm going to get this vector A and draw it as if the tail was here, going out that way to the head, and the same thing with this vector B. Just start with the tail there and go down there, and yeah, that's good. Now that gets me, now I'm unconfused, because I can see that the angle between vector A and B is 120 degrees, because that's tail to tail now, right? Yes, good. So that's good. Now, how am I going to sort out the rest of this mess? Well, probably what I need to do, I've put it in the box here, all options involve basically c squared, so I've got to work out c dot c, guys, obviously, but I have to do it in terms of a and b, because that's what's on the right hand side, and then basically, yes, express c in terms of a and b, and then do c dot c. That's what I'm going to do, c dot c. Okay, put a box around that. That's my strategy. Yeah, hopefully that'll work out. Now, I'm saying that c equals a minus b. Is that right? Yeah, you go along there plus a, and then, yeah, b's running downwards, so that's a minus b to get up to there to the head of c. Right, let's dot it now. Yes, 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 very excellent. Multiply all that out. And remembering that a dot a and b dot b are just a squared and b squared lengths of. Now, I've done, because when you get to there, look, because when you get to there, okay, I can't see that option anywhere. I don't see 2 times anywhere with dots. And they're all weird anyway. They're not just dot products. They've got modular signs around them. So it looks like I've got to basically unpack this a bit, right? That. So I know that A dot B is magnitude of A times magnitude of B times cos of 120, and there's obviously going to be some need to use this 120 degrees up here. So cos of 120 degrees is the same as minus cos of 60, and cos of 60 is a half, so it'll be minus a half, right? Minus a half. So therefore A dot B is going to be, yeah, that's what cos of 120 is. So therefore I'm putting all that in there now into the formula. So what do I get? I get c squared is a squared plus b squared minus 2a dot b minus 2 times magnitude of a times magnitude of b times minus a half. Got it? Yeah, good. So that comes to a squared plus b squared magnitude of plus magnitude of a times magnitude of b, and hopefully that's there. And I think it is there. It's option D. It's option D for you and me. Fills us with glee, yippee. Okay, now look, that was really easy. It looked horrible, but it's really easy if you just keep your head and get a bit of a vector-proofish strategy going. That's what you've got to do. Yes? That's what you've got to do. That's why I'm doing this for you, to help you get your head around what to do. Now, this question looks absolutely beastly, I'm telling you. It's off an exam. But look, you need a diagram. You must have a diagram. First thing I notice is they say these things are position vectors. So I'm going to do them relative to the origin in a schematic representation so I can actually see, for heaven's sake, what I'm supposed to be doing with all this. So the collinear points, P, Q and R, all on the same straight line. And Q lies between P and R. So I'll draw that. Okay, I'll just draw that diagrammatically, not to scale, just a schematic. Okay, relative to the origin, and Q is between those P and R, and there's a ratio of 2 is to 1, this business here, where the magnitude of QR is half the magnitude of PQ, okay? So this thing here is half the size of that thing there, okay? Alright, so now how can we, what do we do to get our heads around what to do here? Well, they say R is equal to, my goodness, R is equal to a big, big question mark. But, look, you're going to have to use this information here. Look, QR is a half of PQ, or PQ is twice QR, yeah? So I think that's the information we've got to use, don't you? And the fact that they're collinear. Yeah, that's going to have to come into it somehow. So let's just put one foot in front of the other and see where we end up here. PQ and R are collinear, and the magnitude of PQ is twice the magnitude of QR. So if they're collinear, that means they're parallel, doesn't it? They're parallel vectors sharing the same common point Q. Q is at the tail of one and at the head of the other, right? Now, if the magnitude of PQ is twice the magnitude of QR, yes, and if they're collinear, in other words, parallel, is what we need to know in this case, therefore we can say that that's what we can say. We can remove the modulus lines and say that PQ must be exactly a scalar multiple of QR because they're parallel to each other. Can't we? Now, that's the leap of logic you've got to get. Right? Now, if you've got to that point now, there, I've got a lovely diagram. I can do vector PQ in terms of all those little PQs and Rs and things, and vector QR the same thing, and then I can make one twice the other and solve it for R. That's what I can do. See? How easy is it? But you know, you must have a diagram. Oh boy, must you ever. So we state this fact in terms of PQ and R and make R the subject. So here we go. PQ is equal to PO plus OQ, which would be that. Do you follow it along? Are you following? That's minus P plus Q, isn't it? Similarly, QR is equal to QO plus OR, which would be minus Q plus R, wouldn't it? Same thing, see? Minus Q all the way down there, plus R all the way up there. You get that? Right, so now what we're going to do now is we're going to write that equation in terms of what we've just got here for PQ and QR, these things. These thingies here, right? PQ is twice QR. Rah, rah, rah. Here we go. Yes, now, and all I've got to do is make R the subject, and hopefully this will all work out beautifully so I can get this question right. There it is. There it is, guys. There it is. There it is. There it is. And I'm just going to make that into the same form as what options A, B, C, D, and E are. Like that. And is that one of them? Looking down the list, being very careful not to get it wrong. Yes. It's option A today. Hooray. Isn't that marvellous? Isn't that marvellous? So now here comes the brain buster for you. What I'm going to do here is I'm going to ask you the minimum, actually just the minimum vector constraints would be necessary to specify the following shapes. I'll give you the geometric and you have to come up with the vector. And I want you to pause the video once you've got all the options A, B, C, and D, and E. They're multiple choice questions and I want you to work out which one is the one. And I've deliberately made them tricky, so you've got to be jolly careful. Okay, we're going to do a trapezium, a parallelogram, a rhombus, and a square. We'll do this one together just to get you the idea. A trapezium, right? A trapezium. Now, I've just drawn it as generally as I can with all the vectors. Nothing's equal to anything or anything like that, or nothing's really specified in terms of what relationships might apply. Now, in terms of the geometric thing, we want AB, line AB, to be parallel to line DC, don't we? Isn't that what you need for a trapezium? Anything else? Don't think so. So, okay, so what about for vector? What do you need to say? Minimum requirement in terms of a vector specification of a trapezium, right? Now, here's the first one, there's the second one, there's the third one, there's the fourth one, there's the fifth one. Now, which of these options is the minimum requirement? Minimum requirement for a trapezium. Okay. Pause the video and come back. Right, you're back? Okay. B equals D. Well, that's utter nonsense, isn't it? They're not the same vector at all. They're pointing different ways, so that's not correct. A equals C. Well, they point the same way, but they're different lengths, so that's not right either, is it? No, that's right. What about C? Now, let's see. Vector A can't be the same as vector B. That's what that's saying. Vector A. Yeah, well, that's true. They're not the same vector because they point different ways, but that's not what's necessary to specify a trapezium, is it? No, it's not. So that's a true statement, but not the minimum requirement to specify a trapezium. Okay, option D. Magnitude of A is not the same as magnitude of C. Well, that's true, but it doesn't. But it also doesn't specify what you need to specify to make it a trapezium, does it? You need to specify actually that A is basically parallel to C, and not just that the lengths aren't the same. You get that? So option D, E better be correct, otherwise we're up the creek without a paddle here, guys. Alright, so C equals KA. So I think that's right. In other words, it's parallel, it's a scalar multiple of A. Ah, how sweet it is. It's true. And it specifies one set of parallel lines, which is what you need for a trapezium. Get it? These are tricky. They're tricky, right? But I'm making them deliberately tricky to try and make you think. Right, a parallelogram now. Okay, what do we need? The minimum vector requirement to specify a parallelogram. Geometric, we need to know that both sets of opposite sides are parallel. That'll do it, won't it? That'll do it. If both sets of opposite sides are parallel, then they have to also be equal in length, opposite sides, if you think about that. Alright, so vector, minimum requirement, A, B, C, D, E, here we go. There's A, there's B, there's C, there's D, Goodness. And there's E. Now, okay. Now I want you to pause the video and you work it out, and then you come back. All right? I'll be here. Right, you back? Okay. Now, minimum requirements to make a parallelogram. Okay, option A. Length of A equals length of B. Length of A. Oh no, that's no good. They have to be parallel, don't they? They have to be parallel, not just equal lengths, right? So that's no good. Vector C equals vector D. Well, that's actually saying that they are parallel and of the same length. Well, I like that. That's good because that will take care of everything. That will take care of everything. Means that if vector C equals vector D, it also means that vector A has to be equal to vector B. If you draw it out, it does. You think about that. Alright, so option C, D, E are supposed to be wrong. Let's have a look at them. Option C, A equals B and C equals D. Well, what? Well, that's correct. Ah, yes, it's correct, but it does give a parallelogram, but it is more than the minimum specification. All you need to really say is that vector C equals vector D. Tricky devil, aren't I? Option D is wrong, because that's saying that the diagonals are at right angles to each other, which does not apply to a parallelogram, only to a rhombus and a square, which is a special case of a rhombus with right angles in the corners. So no, that's wrong. What's this other one? E. Length of A equals length of B. Length of A equals length of B. And vector C equals vector D. Well, it's actually an overspecification of a parallelogram. It's an overspecification of a parallelogram. It does give a parallelogram, but it's more than what you need. It's more than what you need. I was asking you for the minimum requirement. See, that's why I'm tricky. Tricky Wolfie. So, okay, what's this? Rhombus. Okay, rhombus. Let's do that. Rhombus is a parallelogram with all sides of equal length, okay? So, geometric, what do we need to say? Well, we need to say that both sets of opposite sides are parallel, but we also need to say that adjacent sides, that's next door sides, are equal in length. Okay? Yes, that's a rhombus. A rhombus is a special parallelogram, okay, where all sides are equal length. Vector, A, B, C, D, E. Here we go. That. Pause the video. Come back when you're ready, and I'll be here. Right, you're back? Alright. Okay. Right, let's go. Option A. That's saying A equals vector C. Well, that's nice. That's enough for a parallelogram, but it's not enough for a rhombus. Okay? It's not enough for a rhombus. Now, what about option C? Yeah, okay. That option B, I mean. It's saying vector A equals C and B equals D. Yeah, that's okay. That's fine. That also specifies, in fact, it over-specifies a parallelogram, but it doesn't tell you that it's a rhombus. Okay? No good. What about option C? Vector A equals vector C. That gets you a parallelogram, and magnitude of A equals magnitude of B. I like that one. That's a rhombus. That's rhombus. So A equals C specifies a parallelogram, and magnitude of A equals magnitude of B makes all sides equal. So there you got yourself a rhombus, guys. Now, option D. That's actually saying that the diagonals dotted together do not come to 0. And in fact, for a rhombus, they do come to 0, because the diagonals of a rhombus bisect each other at right angles. So, yeah, so the dot product for a rhombus and for a square, beware, equal to 0. Yeah, you need to know that. Can you tuck that away in your memory? You jolly well need to know that. Okay. Now option E. What's that saying? AE equals EC. Yeah, that's saying that that E is the point of bisection of both diagonals, and that's actually correct. But that'll happen with a parallelogram. All parallelograms do that. So that's not enough for a rhombus. It is enough for a parallelogram, but it's not enough for a rhombus. Okay? How are you going? Are you getting it? It's tricky, isn't it? I'm making it tricky, so to make you think. Okay, so let's do the last one now, and then we can get out of here. Square. Beware of the square. So we're saying here for geometric, alright, opposite sides have to be parallel, adjacent sides have to be equal in length. That gets us to rhombus status, but then one angle has to be 90 degrees. That's the extra constraint you need for a square. Okay? So here's your vector minimum requirements. Boom, 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 boom. Pause the video and come back, and we'll see what you think. Right, you're back. All right, now here we go. Option A, vector A dotted with vector B equals 0. Well, that just means that they're at right angles to each other, but that's not enough. That just means that A is perpendicular to B. Other corners could be non-right angles, side lengths could be not equal. It's a bit of a mess. That's no good. What about option B? A dotted with B and B dotted with C. That means that corner B and corner C are both right angles, but it doesn't talk about what's going on in the other two corners, does it? So that's no good. No good at all. That didn't trick us. Hopefully it didn't trick you. Alright, but let's do option C. Vector A equals vector C. Well, that gets us to parallelogram status, guys, and magnitude of A equals magnitude of B. That gets us to rhombus, I think, but it doesn't get us to square. No, beware. It doesn't get us to square. So yeah, that's right. A equals C gets you a parallelogram. Magnitude of A equals magnitude of B gets you to rhombus. It doesn't get you to square, so that's no good. Okay, what about D? So we're saying magnitude of A is magnitude of B equals magnitude of C. A, B, C. Well, that says that A basically does constrain the fourth side as well. It's just telling you they've all got equal sides, but it doesn't talk about the right angle. So again, that gets us to rhombus, but it does not get us to a square. Okay? No, so there. Alright, well this last one better be right. Goodness, otherwise we're really in trouble here. Right, so what are we saying? B equals D. B equals D, that gets us to parallelogram, doesn't it? Magnitude B equals magnitude of C, that gets us to rhombus. And, C dotted with D means that C is perpendicular to D, which means right angle in the corner. Now we're talking. That's a square. That's a square. No problem. Yeah, that's right. That gets us parallelogram. B equals magnitude of C gets us rhombus, and that dotting is the final icing on the cake, which gets us to square. So we're there. We are, and you're a star. How'd you like it? It was fun, wasn't it? I think you should go back and have a good review of all those questions and re-practice these last 4 shapes to feel really confident about what you're doing. And then I think you'll be well on the road to really being good at vector proofs. All right? Thanks for listening, and we'll see you next time.